Hi, my name is Catherine Medina de Villiers, and I have the pleasure of teaching you today about parallel and distributive computing. So, what are we going to learn today? We're going to learn that the computer has a lot of things to do, and there's different ways and techniques it can go about doing a bunch of the tasks. So, we're going to learn about sequential, parallel, and distributing computing, different ways we can go ahead and tackle on these tasks. So we're going to look about the characteristics of a sequential, a parallel, see if we use sequential within parallel, distributed. I like to say distributed. Let's just bring the posse on. And then we're going to talk about comparing the efficiency of the solutions and something called speed up time. Okay. And we're also going to look at, when is enough enough? When is, if we keep on doing distribution or parallel computing, is it really worth it at the end in getting a bang for our buck? So, with no further ado, let's just get down to business here. Okay, so when we're looking at a computer has a lot of things to do. Okay, and you don't realize it because they make it look so suave easy. They have operating systems that's handling all the tasks of the hardware and networking and just kind of taking care of itself. And then on top of that, the computer is trying to make you very happy, the user, with your programs and your spreadsheets and your Word documents and of course your video games, right? So computer needs to schedule these tasks very efficiently. They need to balance it within the CPUs to kind of make it look like you own the whole system, right? So, one of the techniques of doing this is called sequential computing. And sequential computing is taking upon the task like a factory line. It's like one at a time. Okay. It's like, let me do A, then let me do B, then let me do C. Tasks, it's limited hardware. It's probably only on one CPU. It's older hardware. Tasks are dependent. Like, well, task B needs to be done because it depends on, well, excuse me, task A needs to be done because B depends on the results of maybe task A. So that's another reason why we still will use sequential computing. So for example, here we have a task A that's 50 milliseconds, B that's 40 milliseconds, C that's 35 seconds, and we're just going to add it all up, and that whole processing time is going to take 125 milliseconds. So remember, it's like a task on a conveyor belt, one at a time. Okay, let's go ahead and take a look at parallel computing. It's a computational model where the program is broken down in smaller sequential computing operations. Parallel computing, it's a schedules task, normally done on the same computer. It has a parallel portion and a sequential portion. And comparing the efficiency of solutions is done by comparing time it takes to perform the same set of tasks. We'll get more into detail on this. But why parallel computing? It's hardware driven. It's new hardware. We're dealing with the CPU that can have like 64 plus cores on it. So when we look at parallel computing, think of like walking into the classroom and you have a stack of papers and you're like, well, I'm going to just give everybody a paper and you're going to help me grade it all at once and it'll be faster instead of me just going grade a paper, boom, next one, next one, next one, next one, right? So you get like a group of people, you bring on your posse to kind of help you. So your CPUs now are able to do that. It's faster operations that you can do it. A lot of data can be processed. Video gaming goes up substantially, those of you who are my gamers. And the solutions that use parallel computing, they can scale more effectively and efficiently than sequential computing. So parallel computing, let's look at some of the execution time for a parallel computing system. Okay, so let's say, for example, we have here core one, task A, 45 seconds. Core 2 has task B, 50 seconds. But now, instead of just doing boom, 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 Core 3 takes on task C, 25 milliseconds, D 30 with 30 milliseconds. Okay, so that's 55 right there. Task E takes on 40 milliseconds. So your total, the max time you're going to take to perform all these tasks is going to be 55 seconds because that's the core that's going to take the longest. So that's where your longest time is going to be to complete all the tasks. So core A is done in 45 seconds, B 50, you know, E 40, they're saying, hey, what's up, C? C's here, I got 55, but I'm done, versus doing them all one at a time. So comparing efficiency of solutions. So if we look to the left here, we've got a sequential execution time model, one at a time. And remember, this might have to be the way it's done because, B may depend on something that A's got to give it. So it's going to wait up on A to do it. So it's got to maybe be done this way, one at a time. And if you look at the sequential execution time here to the left, it's 125. Well, parallel execution is almost like teamwork makes a dream work. It's like party on. A comes over here 50 milliseconds. B take core 2 takes on B and C. That's 75 milliseconds. Granted, that's the longest it's going to take, but it's still shorter than your sequential time doing all the same supposed tasks. So if we look at speed up time here, we're doing some type of comparison here. So speed up time is going to be our sequential total processing time divided by parallel time. Just a simple equation, just to kind of do that proportional comparison. But one thing you need to know, so if you look down at the bottom of the screen here, it's kind of important. Okay, when increasing the use of parallel computing in a solution, the efficiency of the solution is still restricted by the sequential portion. So remember, when you looked at parallel computing, you know, your time really depended on your total time was still like, waiting on that parallel line up and go, even though you were still maybe putting two tasks on one core. So what does this mean? This means that at some point, adding parallel portions will no longer significantly increase efficiency. So sometimes it's not going to really give you that bang for your buck. So let's look at another one now, distributed computing. Now, distributed computing, you want to talk about having a party of computers. Distributed computing uses the network. Now it's like, I'm going to do a broadband call. Like, hey, anyone out there, more than just what I've got here in my core processing in the CPU, you're going to be tapping into other computers. So that's where you get a mix of sequential and parallel computing coming on here. Examples of distributed computing would be your Google web search, um, Beowulf clusters, things like that we would use to help with the efficiency of those huge tasks. So distributed computing, how is it different from sequential and parallel computing? Well, you're going to use more than one physical computer because remember, this is where you're going to use the network. This is where you're going to call on other computers. It needs a network, okay? So it's a mix of sequential and parallel. Now, the irony of distributed computing is it could take longer because what if your network's down? Remember when we talk about networks? What if everyone's like hopping on the highway, slowing things down? So that's distributed computing may not give you that bang for that buck on the timing. So let's look at a couple of examples. Example one here, you've got two identical processors. You have a particular computer has two identical processors which run in parallel. Okay. Um, must be executed on a single processor. You've got a table of data below. You want to look at this and you want to tell me what is the minimum amount of time you're going to do approximation to execute all three processors when the two processors are run in parallel. So you got two processors, you're going to run in parallel. Okay, you're looking at the minimum amount of time needed. If you could put the video on pause, and then we're going to catch back up. If you said 50 seconds, you're absolutely correct. So, I mean, you can go ahead and throw Y and Z on one processor 40, you'll be done, but you're still holding up for X 50 seconds. Let's look at example two now, kind of in the same vein. What is the difference in execution between running the two processors in parallel in place of running them one after another in a single processor? So you got to watch this question because you're answering the question of what's the difference in time between running the processors in parallel, okay, in place of running them one after the other. Put the video on pause and then we'll catch up with the correct answer. So hopefully you said 25 seconds because when you're running the two processors one after another, then basically you're adding 25 plus 45 and you have 70 seconds. Okay. Running both in parallel, well, you're going to be waiting on the one that's B 45 seconds. A is done already in parallel someplace else. And that difference between the 70 and 45 is 25. So let's recap. Computer needs to handle a lot of things from its operating system to what you want to do with it. We've got parallel, boom, 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 boom. We have sequential, again, one order at a time. We have distributed, is asking other computers to help. So these are some of the things we need to think about. And when you look at parallel while it's trying to do things, it's doing boom, boom in parallel, but it also has a sequential portion, one click, click after the other. So let's look at an example 3 here. Okay, in example 3, your computer has two processors that can run in parallel. So the table below indicates the amount of time it takes for each processor to execute 4 different processes. Describe how the program should assign the 4 processes to optimize the execution time. So if you can go ahead and put that video on pause, and then we'll catch back up with the correct answer. So if you look here, if I on one process put A and B should be assigned to one processor, that gives me 50 seconds. And then C and D to the other processor, there I get another 50 seconds. That's where I'm going to get my optimized execution time. So they're actually two over here, two over there, and they happen to finish off both of them at 50 seconds. How cool is that? Okay, so what should we take away? Take away, computers got a lot of things to do. Operating system, it's the user. Okay, it's getting a lot of tasks. Okay, we look at 3 different models. We have sequential, we're doing one thing at a time. Parallel, you're trying to do some of them simultaneous. Distributed, you're calling on various computers using a computer network. Some of them, like when you're doing sequential, you've got no choice because there's dependencies on other processes. So I'm hoping you really enjoyed today's lesson looking at how different ways a computer can attack and handle all the things it needs to do. Take care.